We're going to start complex numbers and roots. So our objective today, if you watch both videos on complex numbers and roots, is to define and use imaginary and complex numbers. Yes, I said imaginary numbers. We're finally getting to those fun imaginary numbers. And we're also going to solve quadratic equations with complex roots. This will probably be in part 2. Lots of vocabulary words. Push pause and write them down, and as you go through the videos, you will be able to define them. All right, lots of words. I'm going to read through it. You can see in the graph of f of x equals x squared plus 1 right here that f has no real zeros. You remember the zeros are where the parabola crosses the x-axis. And if the parabola doesn't cross the x-axis, there are no real zeros. If you solve this equation, if you set x squared plus 1 equal to 0, subtract 1 from both sides, take the square root, you'll see that x equals plus or minus the square root of 1, which isn't a real number. However, you can find the solutions if you define the square root of negative numbers. And that's why imaginary numbers were invented. Yes, you read that right. They were invented. The imaginary unit I is negative, or square root of negative 1. That's the definition. So we can't take the square root of negative 1, so mathematicians ages ago invented I. You can use the imaginary unit to write the square root of any negative number. Okay, read through that again if that doesn't make sense, and I bet it will. All right, this is the exact same thing presented in a different way. An imaginary number is the square root of a negative number. Imaginary numbers can be written in the form bi, where b is the actual number, and I is the imaginary unit. I is the square root of negative 1. The square of an imaginary number is the original negative number. So, I equals the square root of negative 1. If we have the square root, let's say, of negative 9, we would write that as 3i. That's the bi that you're seeing. Okay, let's try a few. Simplifying square roots of negative numbers. Okay, now what we do is we split this up into its number and negative 1. Okay, we sort of factor out the negative 1. Then you just take the square root of both pieces. The square root of 121 is 11. Okay, 5 times 11 is 55. Doing every bitty step here, which you will not have to do. And you have the definition of imaginary unit. So our answer is pretty simple. Try another one. Again, we're going to factor out the negative 1. Okay, we're going to split that 96 into something that is a perfect square, like 16 and 6. And then actually take the square root of 16, so we get negative 4. I'm just splitting it up into itty-bitty pieces. Okay, keep going. Take the square root of negative 1, which is your imaginary unit. This is just going to take some practice. The more you practice, the easier it gets. Okay, this is just how we've done everything. You split it up into itty-bitty pieces and take square root. Okay, you try this one. Please push pause and try on your own. There you go. Another check it out. There you go again. One more. Okay, push pause and try it. That one had a few more steps, was a little more complicated, but look through the work and I bet you'll understand it. Okay, now we're going to actually solve equations. This is what we've done in the past, but I have negatives instead. So, like you've learned, just going to take the square root of both sides. And by this point, you need to see your answers without splitting it up. You know, last slide we would have gone 144 times -1. Okay, save yourself that step. Okay, you need to see that this is just going to be plus or minus 12i. Okay, you're just saving yourself that step and working through the answer. Try another one. Okay, you need to get your variables on one side and your numbers on the other, and no coefficient in front of your x. So I have x squared equals -18. Square root of both sides. X equals plus or minus 18 works out into 9 times 2. Take the square root of 9, you get 3i square roots of 2. Okay, I broke that 18 up into a 9, a 2, and a -1. I took the square root of 9, I took the square root of -1, and there's a 2 left. That's how I got that. Try this one on your own. Push pause. Okay, next one. Push pause. Okay, that one I had to figure out what the perfect square was. That's a part of 48. That's a factor of 48. And once I did, the answer was... Okay, last one. Push pause, please. This last one was a little tricky, not too bad. I was trying to solve for my variable, and I recognized that when I divided both sides by 9, on this side I have a perfect square over a perfect square. So I didn't want to actually do that division. It just made it harder. 25 divided by 9 is 2.7777 repeating. I didn't want to have to worry about the square root of that, so I left it into 25 over 9. That allowed me to take the square root of 25, which is 5, and 9, which is 3, and gave me a nice, neat, easy number. To check, 5 divided by 3 is going to be the same as the square root of 2.7777 repeating. Good job, guys. There is a part 2 to this video. If you have time, go ahead and watch it.